So today we will be talking about reducibility. In the previous lectures we talked about decidability. So decidability, a problem is decidable if there is a Turing machine that decides the problem. Now, in this part of the course we look at Turing machine is equivalent to algorithm, and in fact it's equivalent to a program. It's just a program written using a general purpose programming language. So, because what's a program? A program is an algorithm implemented using some programming language. So the program is just that code that implements a certain algorithm. An algorithm is just a step-by-step procedure for solving a problem, a sequence of steps for solving a problem. So here in this part of the course, when we say Turing machine or algorithm or program, they're the same thing. But the Turing machine is the theoretical model that we keep referring to. In fact, when I explain reducibility and when I explain the reductions, I will first explain them in terms of programs, actual programs that you are familiar with. Then I will describe them as Turing machines. And in fact, our descriptions of Turing machines in this part of the course are not detailed descriptions. We're not giving a state diagram of a Turing machine. We're only giving a high-level description, which is very much the same as a high-level description of an algorithm. So it's about the same thing. It's not even pseudocode. It's on a higher level than the pseudocode level. It's just a high-level description of the steps. So this is the kind of description that we are using in this part of the course. Now, again, to review, we looked at regular languages, we're looking for algorithms related to regular languages, context-free languages, and Turing machines. And we looked into the acceptance problem for DFAs, and the empty problem for DFAs, and the equivalence problem for DFAs. And all of these are decidable. We showed that all of these are decidable. They have algorithms for solving them. We looked into context-free grammars. The acceptance of context-free grammars is decidable. The emptiness of context-free grammar, determining if a language is empty, was that decidable or not? Yeah, it was decidable. And what about the equivalence of context-free grammars? No, it's not decidable. Now, last time we looked into the first problem related to Turing machines or algorithms or programs, the acceptance of Turing machines. And was that decidable or not? No, it was not decidable. So we did not give the actual proof, but I tried to explain intuitively why acceptance is not decidable, and who can summarize that intuition behind this? What's the intuition behind ATM is not decidable? Accepting. So ATM is you are given a Turing machine and a string, and the objective is to determine M is a Turing machine and W is a string, and TM accepts W, determining if TM accepts or rejects W. What was the intuition? So what kind of program is this? So we're writing an analysis program that takes another program, and it takes an input, and the objective of this analysis program is to tell you within finite time if program M is going to output a yes for string or for input W. So The objective is writing an analysis program that takes program M and input W and determines in finite time if with input W output is yes. So program M is a program that whose output is either yes or no. And the objective of the analysis program is to determine whether program X will output yes if we input W in it. And as we will show today, this is, the challenge in doing this is determining if M is going to halt on W or not. Determining, because if the output is no, if the output on input W is no, then program M may loop forever. And because program M, the intuition is that program M is a general program. Basically, it's written in the same general or in a general purpose language that's as powerful as the program, as the language in which we wrote the analysis program. So the analysis program that we're trying to write and the program M that we're trying to analyze, both are written in general purpose programming languages. Of course, they don't have to be written in the same language, but they both have to be written in general purpose programming languages, or Turing complete programming languages. A language that has all the features that can be implemented using a Turing machine. Okay, the problem lies in the generality of the program that we are trying to analyze. So that program that we are trying to analyze may have all kinds of function calls and recursions and loops, and the conditions for terminating loops or the base conditions for recursion may be very complex. So you just have a loop, and then in that loop, if complex expression break. This complex expression, if the language is general enough, can be very, very complex. Right? It can have many, many function calls or many, many levels of function calls in it. Right? So analyzing it in general is not possible. And analyzing a general program is not possible. Okay, so that summarizes the intuition behind ATM is not decidable. Okay, now today we will look into the other two problems, which are ETM and equivalence of TM, to see whether it's decidable or not. But before that, we will look into this problem, which is the halting problem. So, well, first, ATM is given M and W. M accepts W, where M is a Turing machine, W is a string, and halt TM is given a program M and string W. M halts on W. Now, what does halt mean? It means it terminates within finite time. So halts means terminates within finite time, or in other words, does not loop. Does not loop forever. Okay. Now we will show how, if we assume that ATM, the acceptance is known to be undecidable, how we can prove that the halting problem is undecidable. And this can be proved using what we call reductions. Now, what's a reduction? A reduction is a way of converting one problem to another problem. And in order to explain the concept of reductions, I'm going to use problems, different kinds of problems that you are familiar with. I'm going to use the cubic equation problem. So let's assume that we have a program or an algorithm that solves cubic equations. So a cubic equation is of the form ax cubed plus bx cubed squared plus cx plus d equals 0. So this program, you give it a, b, the coefficients of the equation, a, b, c, and d. And what does it give you? The roots, the values of x, or roots, solutions, or the solution, the values of x which satisfy this equation. So this is a program that solves this equation. Now let's call this problem problem B, or problem A. Why? Now what about the quadratic equation? This is equation problem. Let's call it problem B, where we have e x squared plus ef plus fx plus g, efg equals 0. Now, if I give you this program that solves cubic equations, can you use it to solve quadratic equations? Yeah, you can easily use it. Now, in order to use this solver for cubic equations to solve solver for cubic equations, to use it for solving a quadratic equation, what should you set A to? Yeah, you set A to 0, you set B to E, and you set C to F, and then and this is D, sorry. And you set D to G. So you are given this solver for cubic equations. You use it to solve quadratic equations. So this is a reduction, but this is a very easy reduction because all what you needed to do is to set the values of these coefficients. So in this case, we say that B is reducible to A. So we managed to reduce the problem of solving B into the problem of solving A. Or given a solver for A, we managed to solve B. Now, the notation that we will use, B is less than or equal M. In fact, we don't read it less than or equal. We read it reducible, mapping reducible to A. So we read this as mapping reducible. What does mapping reducible mean? It means that there is a mapping, a function, mapping reducible. There is a function And that function is Turing computable. We can compute it using a Turing machine, or we can compute it using, a general purpose, a program written in a general purpose language, running on a general purpose computer. And we know that, what the operations that a program written in a general purpose language running on a general purpose computer, what the operations are. We know that a general purpose computer can easily do all kinds of arithmetic, add, subtract, multiply, divide, etc. So problem B is mapping reducible to A, or to problem A, if there exists a computable or Turing computable function f that maps every instance of B into an instance of A. So given an instance of B, any instance of B can be converted into an instance of A. By the way, for this example, can we do the mapping in the other direction? Can we map every instance of A into an instance of B? No, we cannot. Because in this case, B is just a special case of A. A is a more general problem than B. Now, this relation, mapping reducibility, is going to exist between two problems or two languages, not only when one of them is a special case of the other, or one of them is more general than the other. In fact, they can be on the same level. They can be different forms of the same problem. So I can give you problem C, for example. Problem C is E x cubed plus fx squared plus gx equals h. So now, intuitively, what's the relation between problem A and problem C? Intuitively, it's the same problem, right? But in two different forms. Now, if I have a solver for A, I can use it to solve C by setting A to E and B to F, C to G, and D negative H. Yes. So this is a very simple reduction. Basically, the conversion, or what we needed to do in order to convert an instance of C into an instance of A, is a very simple procedure, or a very simple mapping function. Why? Because they're very similar. So the more similar the two problems are, the less work you will have to do in order to convert an instance of one to an instance of the other. More similarity, less work you'll have to do. Less similar, you'll have to do more work in order to convert one instance of a problem into an instance of the other. So in this case, we can still say, C is mapping reducible to A. Right? C is mapping reducible to A. And in fact, we can do it in the other direction as well. If we have a solver for C, we can also use it to solve A. So the relation can go in both directions. So C is reducible to A and A is reducible to C, because in this case, A and C are two forms of the same problem, while this bidirectional relation does not exist between A and B. You know, B is reducible to A, but A is not reducible to B, because A is a more general problem. Okay, now how does this help us prove that a certain problem is decidable or undecidable? Now, if problem A, or let's A is polynomially, or let's do B. B is mapping reducible to A. And A is decidable. What can we say about B? B must be decidable because we can reduce any instance of B into an instance of A. So if A is decidable, it means there is an algorithm for solving A. If there is an algorithm for solving A, I can always use it to solve B, because this means that I can convert any instance of B into an instance of A. So this implies then B is decidable. Now, if B is mapping reducible to A, and B is not decidable, what can we say about A? If B is undecidable, what can we say about A? It must be undecidable. A is why? Well, there are multiple ways of answering this. First of all, it's the contrapositive of this. Right? So if B is reducible to A and A is decidable, then B is decidable. This is the contrapositive. So this is the logical contrapositive of that. If B is undecidable, then A is undecidable. Another way of thinking of it is by contradiction. Right? Assume that here B is reducible to A. Now assume that we know that B is undecidable. Now, if I assume that A is decidable, I will reach a contradiction, because if A is decidable, B would be decidable, but it's not. I'm given that it's not. And the most intuitive way of thinking of this is that, you know, this mapping, this notation that we use for denote mapping, it's very mnemonic, because it means that when B is reducible to A, it means that B is less than or equal to A in terms of difficulty. Okay, so B is either easier than A, or at least, or as difficult as A in terms of the difficulty of solving it. So now, if I know that the easy one is undecidable, the harder one, which is A, or the one that's at least as hard, so here A is at least as hard as B, must be undecidable as well. Okay, so the most intuitive way of thinking of this is that this problem is less than or equal to this problem in terms of difficulty. And I know that this one that can be easier or as difficult as A is not decidable, then this one must be undecidable as well. Because A is at least as hard as B. A is at least as hard as B. Okay. Now we are ready to use this to prove that the halting problem is now our objective is assuming that ATM is known to be undecidable prove that halt TM is undecidable. So here, using the reductions, do we need a reduction from ATM to halt TM, or a reduction from halt TM into ATM? Which one do we need? Do we need this, the first reduction, or the second? Do we need to reduce every instance of ATM into an instance of halt, or every instance of halt into an instance of ATM?
The first one.
Why is it the first one?
Because if the one at the beginning that is less than or equal to it, if that's undecidable, then the second part of the equation is undecidable.
Yeah, this is the one that will help us show that halt TM is undecidable. If ATM is less than or equal to halt TM in terms of difficulty, or halt TM is at least as hard as ATM in terms of difficulty, this will help us prove that halt is also undecidable, because a problem that's less than or equal to it in difficulty is known to be undecidable. While if we show this, it will not prove anything. Right? This will not prove anything. It's like, this is known to be hard, and if we show that halt TM is less than or equal to a problem that is known to be hard, less than or equal to it in terms of difficulty, that will not prove anything, because this can be much, much easier. Right? So showing that it's less than or equal will not help us prove anything. Okay, so now we need a reduction from ATM to halt TM. So we need to show that we can reduce convert every instance of ATM into an instance of halt TM. How? Well, let's think about it in terms of programs first, before we think of it in terms of Turing machines. Now, to convert every instance of ATM into an instance of halt TM, I will have to assume that I have a solver for halt TM. So assuming that I have a solver for halt TM, I can use it to solve ATM. So I'm going to show that if I assume that I have a solver for this, I can solve any instance of this. And then this will contradict what is given, which is ATM is not solvable. So you assume that you have a Turing machine R that decides halt TM. So let's think of it in terms of programs. So R, just a program. R that takes another program M and W, and it tells you if if M holds somehow with some magic, if M halts on W, return yes, else return no. Now I'm assuming that I have this magical program or this magical algorithm that solves the halting problem. I give it any program and any string, and it tells me magically. Of course, we will reach the conclusion is that such a program cannot exist. But now we are assuming that it exists, and then we will reach a contradiction with what's given, which is ATM is not decidable. Now let's assume that we have this S that takes M and W, and we need to use this to determine if M accepts W. To use this solver for the halting problem to solve the acceptance problem, all what you need to do is to call this to determine if this halts or not. If it halts, then you run M. If it doesn't halt, you just reject. So what you need to do here, sorry, I was thinking in another problem. So if run R of M and W, you run R, or if and this is the result of R. If result equals no, reject. Else, what? Now, if R rejects, if R says no, it doesn't halt, then I reject the string. Now, if it doesn't reject, if R does not reject, or if the result is yes, it means that it halts, and it will be safe to call M. Else, just run. Just call or return M of W. So, assuming that this magic program that determines if a program halts or not exists, it can help me avoid looping forever, because I can call R and it tells me if R is going to loop on the string. If it tells me with some magic that it's going to loop on the string, then I'm going to reject it without having to loop forever. Otherwise, I will just call M, and I know that M in this case will terminate. Why? Because this magical R told me that M halts on W. So in the else part, I'm guaranteed that M is not going to loop. Because if it loops, I will reject. Otherwise, I will return M. So this means that if you give me a solver for the halting problem, I can use it to solve the acceptance problem. But I know that the acceptance problem is undecidable. Therefore, such a solver cannot exist. So I conclude that this solver cannot exist. Because if I have it, I will be able to solve ATM with it. So this is a solver for halt, and this is a solver for A, acceptance. Okay, so we can write this in terms of a Turing machine now. Given assume that you have a Turing machine R that decides halt. We can build a Turing machine S that solves ATM as follows. S is going to be run R on W, run R on M and W. If R rejects, or if R says that it doesn't halt, reject. Else, simulate M on W. If M accepts, accept. Else, reject. So basically, this kind of conversion or reduction is very similar to the reduction of the two different forms of cubic equations, because these two problems are just very similar. So here what we are saying is if we have a solver for halt, we can build a solver for acceptance, ATM, but we know that such a solver does not exist because this is undecidable. Therefore, a solver for halt cannot exist. But this contradicts the assumption that no Turing machine that decides ATM exists. Therefore, a decider or decider R for halt decider R for halt does not exist. Okay, so basically we're showing that halt is not any easier than ATM, and if you give me a solver for halt, I can use it to solve ATM, but since ATM is known to be undecidable, the solver for halt cannot exist. Okay, so now any questions on this? Okay, so on this topic, things take longer than expected. Okay, so now we will look at the emptiness problem, empty TM, where we are given M and only M, and M is a Turing machine and the language of M equals phi. So this is a problem that we managed to solve for finite automata and regular languages. Is it solvable for Turing machines? The answer is no, because we can reduce ETM to, or we can reduce ATM to ETM. So we can reduce ATM to ETM. Or if we are given a solver for E, we can solve A. So this solver R for ETM, it takes a machine R and it returns, it returns yes, if L of M equals phi, return yes, else return no. Now again, this is a magical machine that we assume to exist, but then we will conclude that it doesn't exist. Because if such a machine existed, we can use it to solve ATM. So how can we use this to solve ATM, the acceptance? S. So this is E TM, and this is A TM. So this takes M and W. Now this is where we need to construct, to transform M into another machine, because if this tells us that, if we call R, and it tells us that, it says yes. If we call R and R says yes, what should we do? What should we return for W? So we're given M and W, and we call R of M. If R of M equals yes, what should we do? Return no, definitely. If R of M equals yes, we return no, because this means that M does not accept anything, right? So if this magical machine tells us that this M rejects everything, then it will reject W. But if it tells us no, does this help us determine if M accepts or rejects W? No, it will not. It says it just accepts some strings, and W can be one of those strings that M accepts, and it cannot. Now this is where we need to transform M into another machine, M1, that takes X, and it says if X equals W, X does not equal W, return no, else return yes. Or return, M of X. Now if I call R, well, first if R of M1 equals no, what does this tell me? If R of M1 equals no,
X is not equal to W.
okay, now does this help me solve this? Now what if R of M1 says yes? Then I know for sure, if R of M1 says yes, I know that M accepts W, because M1 cannot return yes unless the string is W. For anything other than W, it cannot return yes. So if it says no, if R of M equals no, return no. If R of M1 equals yes, return yes. So I changed M such that it can only accept W. And if this R if R of M1 equals yes, which is empty. R returns yes if it's empty. So if it's yes, if it's empty, yes means empty here, then I return no. If R of M1 equals no, then I return yes. Remember that R returns yes if it's empty. So if the length of M1 is empty, If the language is empty, it means that it does not accept the string W because it does not accept anything. And if it's non-empty, then it accepts some string, but I changed M1 such that the only string that can be accepted is this W. So if the language of M1 is non-empty, then W is accepted. Okay. So any questions on this?